So today we're looking at what you could call the ultimate map of reality. We're doing a deep dive into the evolution of the atom.
It's a great topic.
Yeah, tracing that journey from, philosophical guesses all the way to the really mind-bending probability clouds of quantum mechanics.
Well, it's such a fascinating story because it's not just the history of science. It's about humanity slowly realizing that the universe is just so much stranger than our common sense would suggest.
We went from thinking about solid marbles to, what, mathematical ghosts?
That's a good way to put it. And for a very long time, I mean, we're talking about 2,000 years, it was just a hunch.
Right, you had Democritus in Greece and Acharya Kanad in India.
Both independently suggesting that if you just keep cutting a piece of matter, you eventually hit a wall, a piece you just can't cut anymore.
Thomas, the uncuttable.
Or Anu. But that was all philosophy. It didn't become science until, well, much later, 1808, with John Dalton.
And he's the one who brings data into it.
Exactly. He wasn't just guessing. He was looking at chemical reactions, at weights. He saw that elements always combine in these very specific whole number ratios.
Which implies they must be distinct units. That an atom of gold is different from an atom of carbon, and they each have their own fixed mass.
Right. So Dalton gives us the solid sphere model. Atoms are hard, little, indestructible billiard balls.
Simple, clean, and completely wrong.
Well, let's say incomplete. The billiard ball model gets cracked in 1897.
By J.J. Thomson.
Yep. He was experimenting with cathode ray tubes. They're basically just vacuum tubes. And he noticed these mysterious rays were bending toward a positively charged plate.
Meaning the rays themselves had to be made of something negative. He'd found the electron.
Precisely. And that was a huge deal. If an atom has a negative piece inside it, but the whole atom is neutral.
Then there has to be something positive in there to balance it out.
And that's how he came up with the plum pudding model.
Which always sounds a little weird. For anyone listening, think of it like a blueberry muffin. The muffin dough is this big cloud of positive charge, and the electrons are the little blueberries stuck inside.
It's a decent visual, yeah. But it didn't survive Ernest Rutherford's gold foil experiment in 1911.
Okay, so Rutherford starts firing what are essentially tiny positive bullets, alpha particles, at a super thin sheet of gold foil.
And he expected them to just punch right through the muffin. And most of them did.
But not all of them.
Not all of them. A tiny fraction bounced back. Some came straight back at him, a full 180 degrees.
You don't bounce a bullet off a muffin.
You really don't. Rutherford said it was like firing a cannonball at a piece of tissue paper and having it come back and hit you. He realized the positive charge couldn't be a soft pudding. It had to be a tiny, incredibly dense knot right in the center.
The nucleus.
The nucleus. And just like that, the plum pudding model is gone.
And we get the planetary model in its place. The one everyone recognizes. Little nucleus, like the sun, and electrons orbiting it like planets.
It's a powerful image, but it's a complete physics nightmare. There's a fatal flaw.
Go on.
Well, according to James Clerk Maxwell's work on electromagnetism, any charged particle that's accelerating should give off energy.
And moving in a circle is a form of acceleration.
Right. So that electron, as it orbits, should be constantly radiating energy. It should lose speed and spiral into the nucleus in like a trillionth of a second.
The whole universe should have just collapsed instantly.
Exactly. The model was fundamentally unstable, so Niels Bohr comes in and rescues it by introducing, well, a really weird idea.
He introduces quantized states.
Yes. He said, think of it like a staircase instead of a ramp. An electron can be on step 1 or step 2, but it can never be in between the steps.
And it only gains or loses energy when it actually jumps from one step to another.
Which perfectly explains something else they were seeing. Why hydrogen atoms only emit very specific colors of light, red, blue, violet, but not a continuous rainbow.
Those colors are just the energy signature of an electron making a specific jump.
That's it. But even Bohr was still picturing the electron as a little ball on a fixed track. Then Heisenberg and Schrödinger came along and the whole map just got fuzzy.
This is the uncertainty principle.
Yep. They proved you cannot know an electron's exact position and its exact momentum at the same time. The more you know one, the less you know the other.
So the neat little orbits have to go. They're dead.
They're replaced by orbitals. We learned from Louis Broglie that matter can act as both a particle and a wave, so the electron isn't a dot at all. It's more like a cloud of probability, a standing wave.
Right, there's that great analogy of a friend in a pitch black room. You know they're in there, and you might know they usually stand by the door, say, 90% of the time. But you don't know exactly where they are.
Until you turn on the light. Until you make a measurement, before you look, that electron is, in a very real sense, everywhere in that cloud at once.
So just to recap this incredible journey, we start with solid billiard balls, then we move to blueberry muffins, then to mini solar systems, and we end up with clouds of pure probability.
We found that at the most fundamental level of reality, nothing is fixed. It's all just a set of likelihoods waiting to, well, to be observed.
Which leaves us with a final thought for you to chew on. If measuring an electron forces its probability wave to collapse into a single particle at a single point, are we just observing reality? Or is the very act of observation what creates it? That's it for this deep dive. Thanks for listening.